Hello everyone, it's August 21st. Well, I got my monitor. Things get a little bit easier to go around. Wait, hold a second. Why is this so bright? I think I like this one better. Movie, game, warm, cool. I think I like this one better. All right. So I got an easy one today. Number complement. Complement of an integer is the integer you get when you flip all zeros to ones and all ones to zeros. Isn't that just exclusive OR? I think it is exclusive OR. Alright, so I think exclusive OR is... But you have to know the num itself. How do you know that? How do you know? That's a good question. Yeah, there is a way, like negative. If you do a negative and then you do and. No, because if it's a 2, a 1, 0, right? When you get to 1, 1, and 1, 1 is like a 3. It's a 4 minus 1. So you need to know how many digits it has. There gotta be a way to. Man, we can count, right? We can definitely count. But I wonder if there's a way to easily get there. I don't know. I don't know what would be the way to do that, except just to count. Yeah, I mean, we can count. We can say count. Right shift and then count plus plus. Alright, and then this will give you a count, and then we can return 1 left shift count minus 1. And then this thing exclusive OR num. But I feel like there is a better way to do it. Yeah, I feel there's a better way to do it. Actually, let's try 2 to the 31st, because you know it's it's Java, so we have to always be careful. Oh, okay. Yeah, well, I guess it works. Okay. It's not what I wanted. Is there any better way? Mask. This is to flip everything. Wait, what's this? This is flipping everything, right? And this is negate. Yeah, you all have to do some type of operation. Mask left shift 1. Mask smaller than num. Ah, I like this idea. I like this idea. You build up the mask. That's actually quite cool. Or you can bit, yeah, you can do bits. It's fine. Yeah, that's actually quite cool. Alright, so we're basically done for today, and maybe we can go back to, okay, what are we talking about in this one? What do we want? I don't remember what we want. We have one submission, which is Dijkstra. No, this is DSU. This is DSU. It's a union find. Oh, isn't that the Floyd? No, not Floyd Warshaw. Tarjan. Ah, we're looking at Tarjan. What's the problem again? Exactly one island. Minimum number of days to disconnect the grid. And we say as long as we have like 4, we can always disconnect anything. We just can disconnect this, right? Yeah. So what we want to find out is it possible? Because it's either result is a 2, or if it's possible to remove 1, right? Then we just go through everything, and we remove 1 and see how many groups do we have. Do we have 1 group, or do we have 2 groups? So we have a DSU, right? And we have get DSU. Oh, we go through the whole thing and we get a DSU, return DSU, and array we get everybody. Great, we'll get an index and we'll get its and then random ones. DSU have num regions. Yep. Unrelated regions formed by yes. If it's larger than 1, we already have more than 1 region with 0. Otherwise, we'll go through every one of them. We set it to 0, go through this, we check, right? And then we return this. And we have its indices because we need it for this purpose, for doing the DSU. And then if we cannot break the island by removing just 1 cell, we can always break the island into 2 cells. Yes, that is the thing. Okay, so I have this algorithm called Tarjan. I definitely done Tarjan in the past. An articulation point is a cell that will split the island in 2 when it is changed from land to water. Yeah, it is just a critical node. A critical node that can break a fully connected, right? It can break a fully connected graph. If a given grid has an articulation point, we can disconnect the island in 1 day. Tarjan's algorithm efficiently finds articulation points in a graph. The algorithm uses 3. Okay, so we have Tarjan, right? The earlier one we were looking at, what's it called? It's called Floyd-Warshall. Floyd-Warshall is to find the minimum steps or minimum weights between any pair. That's Floyd-Warshall, which is quite straightforward. You go through all of them, you go through the third one, and then if it gets smaller, you just update. Yeah, that's Floyd-Warshall. Tarjan uses 3 key pieces of information for each node. Discovery time, lowest reachable time, and parent. The discovery time is when a node is first visited during the DFS. Lowest reachable time is the minimum discovery time of any node that can be reached from the subtree rooted at the current node, including the current node itself. Parent is the node from which the current node was discovered during the DFS. A node can be an articulation point in 2 cases. A non-root node is an articulation point if it has a child whose lowest reachable time is greater than or equal to the node's discovery time. This condition means that the child and its subtree cannot reach any ancestor of the current node without going through the current node, making it critical for connectivity. The root node is an articulation point if it has more than 1 child. That is true. Removing the root will disconnect these children from each other. Okay, I have to read the first one again. Discovery time is the lowest reachable time when a node is first visited during the DFS. The lowest reachable time is the minimum. Now, the discovery time is when a node is first visited during the DFS. From where? Who is the node? Who is the root? The lowest reachable time is the minimum discovery time of any node that can be reached from the subtree rooted at the current node. So I am at a current node. Then we need to find the lowest reachable time of a node. And the parent is the node from which the current node was discovered during the DFS. So we have a parent, we have the root, and then we go through, and for each one we can also do the lowest reachable time. And it says a non-root node is an I heard Jimbo make some noise. An articulation point, if it has a child whose lowest reachable time is greater than or equal to the node's discovery time. The child cannot reach any ancestor of the current node without going through the current node. Whose lowest reachable time is greater than or equal to the node's discovery time. Huh? If a child Alright, I don't understand this Tarjan at all. I think I have to Google this. I definitely saw this before. Yeah, look, I've done this before. Strongly connected component algorithm. DFS search produces DFS tree. Strongly connected components form subtrees. If we can find a head of such subtrees, we can print store all the nodes. No back edge. Are you kidding me? I'm not implementing this for sure, but I do want to understand. Hard to find strongly connected component. That's not exactly what. Articulation. Okay, let's try this one. Articulation points and bridges. Let's define what an articulation point is. We say that a vertex V in a graph G with C connected components is an articulation point if its removal increases the number of connected components of G. In other words, let C prime be the number of connected components after removing vertex V. If C prime larger than C, then V is an articulation point. Okay, yeah. Totally makes sense. How to find articulation points? Naive approach. For every vertex V, if I remove it, if the number of connecting points increases, then V is add V back to G. Exactly. That's our algorithm. It's V times V plus E. Tarjan is V plus E. we need to know that an ancestor of some node V is a node A that was discovered before V in a DFS traversal. Okay, I get this. In a graph G1 shown above, if we start our DFS from A and follow the path to C, ABC, then A is an ancestor of B and C in this spanning tree generated from example of DFS spanning tree of a graph. So this DFS spanning tree, A C D B, A B D C, A B C D, A C B D. Yep. Now that we know definition of ancestor, so A is ancestor for everything, C is ancestor of this, but in this case B is ancestor of a C and D. Okay, that makes sense. Let's say that there is a node V in some graph G that can be reached by a node U through some intermediate nodes, maybe non-intermediate nodes, following some DFS traversal. Okay, V can be reached by U. If V can also be reached by A equals ancestor of U without passing through U, then U is not an articulation point, because it means that if we remove U from G, we can still reach V from A. That is correct. Hence, the number of connected components will remain the same. So if we can conclude that only two conditions for U to be an articulation point are if all paths from A to V require U to be in a graph, I agree. If U is the root of DFS traversal with at least two children subgraph. Yeah, if you have two children, if you disconnect it, if it's the root, right? But the children has to be disconnected from each other. Then we can break conditions 1 into two subconditions. U is an articulation point if it does not have any adjacent node V that can reach A without requiring U to be in G. If it does not have an adjacent node V that can reach A without requiring U, or U is not articulation if it is a root of some cycle. B is an articulation point because all paths from ancestor to B to C require B in, but this is not. B is not an articulation point because there is at least one path. B is an articulation point since it has at least two children subgraph disconnect from each other. First thing we need to know is if some node A is ancestor of some other node V. For this, we can assign a discovery time to each vertex V in the graph based on DFS so that we can know which node was discovered before or after another. If in G1 with ABC, the discovery time will be 1, 2, 3. With this, we know A was discovered before C. Now we need to know if some vertex U is an articulation point. So for that, we will check the following conditions. If there is no way to get to a node V with strictly smaller discovery time than the discovery time of u following the DFS, then u is an articulation point. If there's no way to get, which means in this traversal, you have to go through u in order to go to v, right? Because if there exists some other node, right, there's no way it can get to v via something was smaller. That means you can get to v via a different route. No way to get to node v with strictly smaller discovery time than the discovery time of v. If u following the DFS, then u is an articulation point. It has to be strictly before, because if it is equal, it means that u is the root of a cycle. It is equal, it means that u is the root of a cycle in the DFS traversal. Cycle. Okay, yeah, I agree. Which means if you can, if v can only be reached by the same as u or larger than u, the discovery time, right? No way to get to v with strictly smaller discovery time than the discovery time of u. So we go through, we have discovery time, right? And then v has a discovery time, and then u has a discovery time, right? Some u, and then we go through all different types, and we figure out that there's no way that u has the smallest discovery time among all of them. For every node u, we have to find a node v with the least discovery time that can be reached from u following some DFS, which does not require to pass through any already visited nodes. For every node u, we have to find a node v with the least discovery time that can be reached from u. We can use BFS for that, following some DFS traversal path, which does not require to pass through any already visited nodes. I still don't understand. I still don't understand this. I agree, all the paths. So if we set up a route and then we do all the DFS, all different DFS that get to V, and each one we can get, the discovery time. And then what? If some U is in, there's no way to get to a no V with strictly smaller discovery time. That is good. So discovery time of U, if we have a node whose discovery time is smallest when you reach V. So I have a different way to reach V. And in all these ways, there's no way to get to a node V with strictly smaller discovery time than the discovery time of U. Which means if we start from a root, when you go to V, right, the discovery time of V is always larger or equal to the discovery time of U. Right? So we can find all the discovery time over V, and among all the others, if we have a node U whose discovery time is always smaller than V, which means U is always, in all conditions, U is the ancestor of V. So if you remove it, then okay, that's understandable. As if for every node U, we have to find a node V with the least discovery time. Can be reached from U, which does not require to pass through any already visited nodes. I don't understand what this means. Low? I don't know what adjacent node means. Yep. What the hell is low? Alright, I don't understand this one. Let's try another one. Tarjan articulation. Alright, let's try this. Okay, the ideal is DFS, A vertex U is the parent if uses I agree. In a DFS tree, a vertex U is an articulation point if one of the following is true. U is the root of this tree and it has at least 2 children. In the DFS tree, if something has 2, but what if these 2 are connected? Then it has only 1. Yeah, that makes sense. Yeah, because if say 1 and 4 are connected, if we go from 3, we will have actually this go here, DFS. I don't know. U is a root and it has at least 2 children. The root of the DFS tree. If you are the root of a DFS tree, and you have 2 children, who decides what is the DFS tree? What is the root of the DFS tree? I thought you can pick whichever, right? U is not the root and it has child V such that no vertex in the subtree. Hold on. U is not the root of a DFS tree. And it has a child V such that no vertex in the subtree rooted in V has a back edge to one of the ancestors in DFS tree of U, and it has a child of V such that no vertex in the subtree has a back edge to one of the ancestors in the DFS tree of U. Okay, let's see this. For verse 3, which is not the root? What do you mean by which is not the root? What do you decide what is the root, what is not the root? Vertex 4 is the child of vertex 3. No vertex in the subtree rooted at 4 has a back edge to one of ancestors of vertex 3. Thus, on removal for vertex 3 and its associated edge, the graph will be disconnected and the number of components will increase, as the subtree rooted at vertex 4 will form a separate component. Hence, vertex 3 is an articulation point. Now consider the following graph. Again, the vertex 4 is the child of 3 for the subtree rooted at vertex 4. 7 has a back edge to one of the ancestors. Thus, this subtree will not get disconnected, because if you do this, we have a back edge. Okay, yeah, that I understand. Right, that I understand. There's no child V of vertex 3 such that subtree rooted at vertex V does not have is not a decision point in this case. Maintain a parent array where parent U stores the parent of vertex U to check if U is the root of the DFS tree, and attitude. For every vertex, count children. If the currently visited vertex is a root and has more than 2 children, print it. I still don't understand this. What if we have like a square and we start from something? Count children. If the current visit is a root, which means it doesn't have parent, I still don't understand. This has at least 2 children part. I don't understand. Like what do you mean by if U is the root? I probably have to look at the implementation to understand this thing. U is not the root of the DFS tree. So yeah, we produce a DFS tree, right? And then a U is not its root, and it has a child V. Okay, it means adjacent, such that no vertex in a subtree rooted with V has a back edge. So the discovery time of vertices for every node U, okay, for every node U, find out the earliest visited vertex. For every node U, find out the earliest visited vertex that can be reached from the subtree rooted with U. So for every node U, find out the earliest visited vertex that can be reached from the subtree, basically the minimum discovery time of all the nodes is rooted with U. So we maintain an additional array low such that low U will equal the minimum of discovery U. Huh? W is an ancestor of U, and there is a backhatch from some descendant of U to W. What? I have no idea what this low is. We'll have to find out what this low is. Okay, this is a utility, and what we do, visited, number of vertices, distance, low. Yeah, I still don't understand what this low is. Discovery time of U. Call the recursive helper function to find a division point. Okay, so we go through DFS tree rooted with I. If has not been visited before. Okay. Then we do it. If it has been visited, we don't do it. If it has been visited, we don't do it. So we pick a node. Now we do DFS. Okay. Children of the current node. We set the visited to true. Initialize discovery time. Discovery of U. Low of U. I don't know what low of U is. We'll see. Okay. All the vertices adjacent to this. So this V is adjacent. If V is not visited yet, then make it a child of U in DFS tree and a recursion from it. So U, V's parent is U. Children plus equal 1. So U has a children, right? And we will keep going. Otherwise, we check if the subtree rooted with V has a connection to one of the ancestors of U. So we already visited this, right? We visited this, and this is U's discovery time, and this is the lowest of V's discovery time. If the subtree rooted with V has a connection to one of the ancestors of you. And V is its children. U is a root. And has 2 or more children. Yeah, that's what I don't understand. That's what I don't understand. If you, like, what if I start from 3? Because I can definitely start from 3. Or like, this is 0, I start from here. And it doesn't have any parent. And I do this, and it has 2, and then we say this is a, yeah, this is what I don't understand. Because everybody starts from -1, right? And when you set it to true, you don't unset it. If U is not root, U is a root of the FS tree and it has 2 or more children. Yeah, that's like, I don't know. What was I missing? I really don't know what this is trying to say. U is an utility point if it's a root, but you decide on who is a root. That's the thing, you decide, right? You are here, you go through every single node and you decide who is the root. And I can just make this to be 0, right? If I make this to be 0 and we start, but then we don't go through this. Okay, if I start from here, then we go here, right? Then this has parent as this, then we go here, then we go here, then we go here. But this one's already visited, right? We have a cycle, right? So this one already visited. What happens if you already visited? Huh. you will do it again. You will set it to true again. Okay, so if I go around and visit you again, right, we'll set it to true. We'll have a new discovery time. Right, we'll have a new discovery time. No, before. So, so we're here, right? Okay, this is the root, and then we go here, and then we go here, and then when we visit one, we haven't visited this one before, right? And we set, and 3 is its child. If this is false, but now it's true, right? Now it's true. Then you go down, update low value of u for parent function calls. And v is not equal to, what if v is, again, yeah, I still don't understand. We don't really change this parent thing. Parent v equal to u. Because visited is not false, because I already visited it. Yeah, I don't understand. Maybe I need to, what's this graph? 1 to 0, 0 to 2. Can we, yeah, we probably need to, I need to run this to have a better understanding. Yeah, this I don't understand. If u is a root, we can make anything your root. Like seriously, you can make anything your root. And it does say you go through the whole thing, right? It does say you go through the whole thing. You go through all the DFS first. And when you go through the DFS, right, you go through, so you can go here, right, you go here, you go this cannot go anyway, so you go here, this cannot go anyway, go here, here, or here, go back, right? You do go back, but once you go back, right, 7 1, you go, I'm at 1, so u is 1, I'll visit it, and we get its discovery time, so u is 1, and then v is 3, and this one is true, so we don't go through this, right? Then we go through here, parent u is not equal to, because parent is not equal to, then low u goes low u and then discovery v, whatever it is, right? We run this, and then that's it, right? Then after we come back, after we run through all this, parent u is still -1. All right, this one requires a lot more understanding. So far, I don't understand it. But this is simple enough that I think I can run this in my system and then just, get an idea of how this one works. And then, in fact, maybe I can do it right now. If I can just say, let's say tarjan.py, okay, and then we just copy the whole thing, but of course we change some stuff. I want this. Okay, I want this. How do I implement this? Add edge. Ain't no 0. Okay, so I need, let's say 0, 1, 2, 3, 4, 5, 6, and yeah, this should be 6. Okay, this is my, so we have edge 0, 1, so we have 0 to 6, we have 7, okay, so 7, we have 0, 1, 1 to 2, 1 to 6, okay, 1 to 2, 1 to 6, 2 to 3, 3, 4, 3, 5, 3, 6, 3, 4, 3, 5, and 3, 6. Okay, let's run this by, oopsie doodie, that's wrong. That is wrong. We want to do this. Okay, Python 3 and Tarjan. Artificial point this graph 1 and 3. You see that? This is wrong. This is wrong because 3 is not. Oh wait, hold on. My bad. No, not this one. This. Oh, it's correct. What? What in the world? All right, let's rename them. Yeah, let me rename them. Let's name this as 0. Okay. And we name this as 2. So we have 2 to 1. Right, 2 to 1. Wait, hold on. So basically, all the 0 has to be 2. All the 2 has to be 0. Right? 2 has to be 0, 0 has to be. So 0 has to be 2. 2 has to be 0. Right, 1 to 0, 0 to 3, everybody's the same, okay? Let's try. Oh, wow. That is, okay, I did not expect that. How about I do self.ap utility 0 visited AP parent. You are kidding me. Huh. This is interesting. Did I understand this one wrong? And of course, there's also a second part I still don't understand. What is low U anyway? Low U is low U and low V. So V is its children, right? V is its children, and low I think it's the some sort of the minimum, right? Some sort of minimum discovery time. So if the subtree rooted in V has a connection to one of the ancestors of U, right? then the discovery time of v must be no bigger, right? No bigger than discovery time of u. If u is not root and the low value of one of its child is more than the discovery of u. This is actually contrary to what I was thinking. For v in graph u, and if v is not the parent of u. Okay, so we just don't go back, right? If v is not the parent of u, and v has been visited before, and low u is minimum of low u and discovery v. And note that the discovery time, it's keep running. So like the discovery time is updated for each run, but the low is also updated. What in the world? All right, I don't understand. I have to do this again. All right, I'll see.